We're going to look at a few topics related to memory organization. So memory, as you know, is stored as a collection of bits. Each bit is binary. It can either take 0 or a 1. A collection of 8 bits is a byte. A collection of 16 bits is generally called a word. But in some cases, in some systems, 8 bits is called a word. In some cases, 64 bits is called a word, and so on. And word is generally the standard length of of a unit of memory when we are talking at the CPU register level. So any data transfer that happens between registers and memory or vice versa generally happens in terms of words. So you transfer one word at a time or two words at a time, and not one bit or one byte. So that's some terminology. So accessing the memory is done by specifying the address, and this is one point to be remembered, which is so this is the size of the memory is given by 2 to the power k, where k is the number of bits used to hold a memory address. So here we have a big example, 16 bits, but we'll take a small example. So let's say you have 3 digits which you can fill with zeros or ones. The total possible combinations are 8, right? From 000, 001, so on up to 111. There are 8 possible combinations, and that is given by 2 power 3. So if I tell you you have 3 digits to represent a memory location, there are 8 different memory locations you can represent, ranging from 000 to 111. Similarly, if I give you k bits to hold a memory address, you can represent 2 power k addresses. So, and within those k bits, there are 2 ways of representing your address: Big Endian and Little Endian assignments. So in Big Endian, the lower addresses are used for the most significant bytes. In Little Endian, the lower addresses are used for the least significant bytes. So we'll take this example to understand what that means. So this is your register. It has some number of bytes. The addresses are, let's say, A plus 1, A plus 2, A plus 3, and so on. And this is the data it contains. Now in Big Endian notation, the smallest memory address contains the most significant bytes. So let's say you take a number, a normal decimal number, 98765. Here the most significant digit is the one which has maximum place value, 9 here. And why do I say it is most significant? So your number is 98765. Now let us say I am transmitting this number to someone. It's a code sort of, and one of the digits gets changed because of the signal getting corrupt or something. If my 9 gets changed into something else, that is when I'm going to lose the maximum information as compared to when my 5 gets changed. So if my number is a 98765 and the 5 becomes a 1, it becomes a 98761 because of some corruption, then I only lost like 4 units of data. 4 units, not 4 units of data as such, but the difference is only by 4 units. But if my 9 becomes a 1 instead, if it becomes 18765, then I'm losing over a range of 80,000, because 98765 minus 18765 is 80,000 if my math is not too wrong. So the idea being, whichever digit has the highest place value, that is going to be the most significant digit, whether you're talking about the decimal system or binary system, hex, whatever. So in Big Endian, that most significant digit takes the smallest memory address. So if my memory address is going to be 10, 11, 12, 13 and so on, and I have 98765, my 9 will be stored at location 10, 8 at location 11 and so on. In Little Endian, it's just the opposite. My 5 will be stored at location 10, 6 at location 11 and so on, in the other way around. So these are just 2 different ways of representing things. We do not go into which is better, which is worse and all that in this course. It's just to know that even within the given k bits, 2 power k addresses, there are different ways in which things can be represented. So that's it about Big Endian and Little Endian assignments.